So welcome everyone to the last session of the day. We're gonna start off, so it is now 3:30, I don't know what time zone I am in, so 3:30 Pacific time, but we're gonna start off. So the first speaker we're gonna have for today is Bronwyn Reichardt-Chu from Swinburne University. Bron, do you wanna share your screen? And we'll be speaking on mapping outflows in starbursting disk galaxies with DUVET.
Thank you. Okay, so the DUVET team have been using KCWI to investigate star formation feedback in starbursting galaxies. Feedback is a major part of the star formation process. So we know from observations that energy from supernovae and from young massive stars gives the surrounding gas turbulence, which affects future star formation. We also know that simulations can't actually reproduce basic properties of galaxies without including feedback. But we don't understand the details of how feedback works or the driving mechanisms behind it. So current feedback models actually fail in extreme starbursting galaxies. And since the majority of stars in our universe were formed in extreme starbursts at redshifts between 1 and 3, if we don't understand how feedback works in these environments, then we don't actually understand how the majority of formed stars in our universe were formed. So DUVET is a Swinburne-led survey of galaxies from our local universe, which match the properties of galaxies at redshift 2. So here we have plotted the star formation rate against the stellar mass. In grey, we have SDSS sample galaxies, and the dashed line shows where the main sequence lies. Blue points are our DUVET galaxies. So DUVET galaxies are chosen to have star formation rates which are 5 to 15 times the main sequence. They're also chosen to be compact, which means that they have really high star formation rate surface densities. So they're starbursting galaxies. They're also chosen to be disks, and we exclude anything which has a major merger. Because these galaxies are in our local universe, they fit really well into KCWI's field of view. So DUVET aims to observe around 30 of these galaxies. So far, we already have 25 observations using Keck time, which has been contributed through Swinburne, NASA, UC, and Caltech. And we have one more night planned in 2020B. We also have data from GMOS and from ALMA, and many of our targets have been chosen to overlap with HSDCOS observations. This means that we will be able to compare studies of feedback across many different wavelengths. So using KCWI, we're making resolved observations of feedback processes and other galaxy properties, which until now have mostly been studied in single galaxy measurements, but we're doing this in a resolved way. So DUVET aims to understand feedback processes on multiple levels. Firstly, we want to understand the stellar population where the feedback is actually taking place. So our data allows us to map faint emission lines like O34363 and helium-2 4685 across our galaxy disks. These lines are sensitive to the initial mass function and the binary fractions of the stellar population. Secondly, the stellar feedback from these stars kicks out gas into the surrounding galaxy halo. And we want to understand how this gas interacts with the surrounding CGM. So to do this, we're mapping the strong emission lines out to really large radius. And thirdly, we're mapping outflows directly. So outflows are an observational tracer of star formation feedback. By comparing outflow kinematic properties to physical galaxy properties, we're able to understand better how the feedback works and the driving mechanisms behind it. So this is the project which I am leading for DUVET. I'm using double Gaussian fits to emission lines to separate the emission from outflows from the emission which is coming from the galaxy. And using this, I'm able to map the kinematics of outflows across galaxy disks. So from local observations of galaxies like M82, what we would expect is that star formation-driven outflows originate in the center of galaxies and flow outwards in a biconical distribution. However, in our pilot target galaxy for DUVET, what we're observing is that there's the signature of outflows across the entire galaxy disk of our pilot target. So here I have plotted our pilot target, IRSO-8, showing the spaxels from KCWI where we see evidence for outflows with maximum outflow velocities ranging from 100 to 500 kilometers per second. The white contours show the galaxy continuum out to the edge of the stellar disk. And what you can see is that this is not really a biconical outflow. This is a very different geometry from what we see locally. So our observations suggest that in extreme starbursts like those at higher redshift, there's a more complex relationship going on between the outflows and the surrounding CGM. They also suggest that the movement of gas around galaxies may work very differently at high redshift than it does locally. But we don't just want to understand the geometry of the outflows. We also want to understand the driving mechanisms behind them to understand how feedback really works. So here I have plotted the maximum outflow velocity against the star formation rate surface density for all spaxels in IRSO-8 where we see a signature of outflows. I have also plotted two possible models which represent the possible driving mechanisms behind these outflows. So we have energy-driven winds. These are outflows driven by supernovae feedback. And we have momentum-driven winds. These are outflows driven by radiative feedback from young stars. And we can see that at least for our pilot target, IRSO-8, these outflows seem to be driven by feedback which is coming from supernovae. So the DUVET survey is using KCWI to make resolved observations of outflows in starbursting galaxies. And using these, we're understanding feedback processes better. We're finding that outflows cover the entire galaxy disk in our pilot target, IRSO-8, which is very different to what we see locally. And we're finding that outflows are following an energy-driven feedback model. Thank you.
Right on time. Thanks for that talk, Bron. So just a reminder, if anybody has any questions, please use either the Q&A, the chat, both through Zoom, or you can do this through the Slack. So while we wait
Harry,
to
I've
see
got
if there's...
one.
Okay, yes, John?
So Bron, when KCRM gets installed, presumably you'll be able to add things like H-alpha and various other lines to this. Can you speak to how that might add to the fun in DUVET, or is there intent to use KCRM with DUVET, or what's your plans with KCRM if possible?
I'm not sure that we have yet plans for KCRM. It would definitely be interesting to use. H-alpha would be really useful. At the moment we've got H-beta, obviously, so that's been good. But yeah, getting as many lines as possible to trace the outflows in as many lines as possible is really good, because then we can trace different phases of the outflows.
I also have a question. Do you have plans to increase the sample size? So you said you've had 30. Are you planning to look at other galaxies after this?
At the moment, we're just working on the galaxies which we already have. The aim is to get 30. We've got 25 at the moment. I think if we can get more telescope time, then that's always good. But yeah, we're focusing on the 30 that we've got at the moment.
Okay, thanks. Okay, I don't see any other questions. So I think we'll wrap up there and move to the next speaker. Thanks, Bron.
Thanks.